Christ University Department of Mathematics proudly presents another video lecture on Convergence of the Derivatives, taught to you by Professor Joseph Varghese.
Given a sequence of functions that is converging to a limit function, the derivatives need not converge to the derivative of the limit. This is the whole point of discussion we are going to have now. Let us go with an example in the beginning. Define fn as sin nx over root n. It is defined for every real number. Let us consider the limit as f of x, that is, limit n tends to infinity, fn of x is f of x. Since sin nx is a bounded function and is bounded by 1, we have the limit is equal to 0 as n tends to infinity. Therefore, fn of x converges to 0 as n tends to infinity for all x which is real. Differentiating the sequence as well as the limit with respect to x, we have fn dash of x is equal to root n into cos nx and f dash of x is equal to 0. Now, let us consider this limit as well as the value of the derivative at the point x is equal to 0. At x is equal to 0, we have fn dash of 0 is equal to root n and f dash of 0 is equal to 0. But limit n tends to infinity, fn dash of 0 becomes infinity, whereas f dash of 0 is 0. Therefore, the derivative of the sequence of functions for this particular function is not converging to the derivative of the limit. So, this prompts us to impose conditions upon which where the derivative of the functions converge to derivative of the limit. These are the conditions what we are going to have. Let fn be a sequence of functions differentiable on the interval ab. Let fn converge for some point x0 on the interval ab. Let the sequence fn dash converge uniformly on the interval ab. Then we have the sequence fn converges uniformly on the interval ab to a function f, and the sequence fn dash converges to its derivative on the interval ab, that is f dash, that is, limit n tends to infinity, fn dash of x is same as f dash of x. Let us go with the proof. Let us choose an epsilon greater than 0. Given also that the sequence is differentiable on the interval ab, define a new function gnm of x as fn of x minus fm of x. Of course, we could see that gnm is differentiable, and since the sequence fn converges for some point x0 on the interval ab, we can choose an n0 such that for all n greater than or equal to n0 and m greater than or equal to n0, we have mod of gnm of x0 is less than epsilon by 2, and for all t belonging to the open interval, t belonging to the interval ab, mod of gnm of t is less than epsilon by 2 into b minus a. Since fn is differentiable on the interval ab, by applying the mean value theorem, we have mod of gnm of x minus gnm of t is less than or equal to gnm dash of t into mod of x minus t for all t comma x on the interval ab. Therefore, mod of gnm of x minus gnm of t is less than mod of x minus t into epsilon by 2 into b minus a, that is less than or equal to b minus a into epsilon by 2 into b minus a, that is less than or equal to epsilon by 2. Using the previous equations, we get mod of gnm of x is then less than epsilon for all x on the interval a comma b and for all n comma n greater than or equal to n naught. That is, writing the equivalent terms of gnm of x, we have mod of fn of x minus fm of x is less than epsilon for all x on the interval a b and for all n comma m greater than or equal to n naught. This implies that sequence fn converges uniformly on the interval a b. That is, limit n tends to infinity fn of x is equal to f of x for all x on the interval a b. We have just now seen that the sequence fn converges uniformly to f on the interval a b. The question remains is, will the derivative of the sequence fn dash of x converge to f dash of x? Let us see that. Now choose a point x from the interval a b, and for another point t not equal to x on a b, we define two new functions as phi n of t is equal to fn of t minus fn of x over t minus x, and phi of t as f of t minus f of x over t minus x. Since fn is differentiable on a b, we have limit t tends to x fn of t minus fn of x over t minus x is fn dash of x. That is, substituting the value, we get limit t tends to x phi n of t is equal to fn dash of x for all n is equal to 1, 2, 3, etc. up to infinity. Let us consider the convergence and check whether it is a stronger convergence or not. Mod of phi n of t minus phi m of t is equal to mod of fn of t minus fn of x over t minus x minus fm of t minus fm of x over t minus x for all t not equal to x, and this is equal to fn of x minus fm of t minus fn of x minus fm of t over t minus x. That is equal to mod of gnm of t minus gnm of x over mod of t minus x. This is less than epsilon by 2 into b minus a from the previous result what we had seen earlier. And this is true for all n and m greater than or equal to n naught. Therefore, the sequence phi n converges uniformly on the interval a b. We need to evaluate what exactly this particular limit function. We have already seen that fn converges uniformly on a b to the function f. Therefore, limit n tends to infinity phi n of t is equal to limit n tends to infinity fn of t minus fn of x over t minus x, that is equal to, applying the limit, f of t minus f of x over t minus x, and that is equal to phi of t for all t not equal to x, and this implies that the convergence was uniform. Since the sequence phi n converges uniformly to phi of t, and also we had seen that limit t tends to x phi n of t is fn dash of x. Therefore, we could see that limit t tends to x and limit n tends to infinity phi n of t is equal to limit n tends to infinity limit t tends to x phi n of t. So, applying the limits, we have limit t tends to x phi of t is equal to limit n tends to infinity fn dash of x. This gives us a result that f dash of x is equal to limit n tends to infinity fn dash of x. Therefore, we have seen that upon the conditions we have listed earlier, the derivative of the sequence is converging to the derivative of the limit. Thank you.